Section 2.7, from U to A. This section generalizes the results we had for upper echelon matrices U to the original matrices A, from which U is obtained using Gaussian elimination. Here's a remark. The principle of conservation of dimension, which says that the dimension of the null space of a transformation T plus the dimension of the range of T equals to the dimension of U, where U is the space we are mapping from. And a special case for matrices that says that for P by Q matrix, Q equals to the dimension of the null space of A plus the dimension of the range of A. These are also written in many books as rank of T plus nullity of T, where rank means the dimension of the range and nullity means the dimension of the null space. That equals to the dimension of V. And also we can restate the matrix version. So this V should be U. And the matrix version is that the rank of A plus the nullity of A equals to Q. And then these are called many times Rank-Nullity Theorem. The following theorem is an analog of lemma U, was denoted by before. Let's go back to see what this is. So this is about upper echelon form matrices with K pivots in them that are P by Q matrices. And the lemma stated that K is less than or equal to the minimum of P and Q. And if K equals to Q, then U is left invertible if and only if, and if and only if the null space is 0. And similarly, K equals to P if and only if U is right invertible, if and only if the range of U is the whole FP vector space. So we reformulate this lemma for general matrices A of size P by Q instead of upper echelon matrices. We already stated that the general matrix A can be transformed into upper echelon form using matrix multiplication G times A equals U, where G is an invertible matrix. So this theorem actually follows from this previous lemma, but we give a direct proof of it anyway. So the theorem is that if A is a P by Q matrix, then the rank of A equals to P if and only if A is right invertible, if and only if the range of A equals to the whole FP vector space, and the rank of A equals to Q if and only if A is left invertible, if and only if the null space of A is just the 0 vector. The third part is that if A has both left inverse B, which is Q by P then, and right inverse C, which is supposed to be then Q by P also, then B equals to C, and P equals to Q, and A has no other left or right inverses. So the first part, the proof of the first part, if we have AX that's in FP space, and this is true for all X in FQ space, that means that the range of A is a subset of the FP space. So that means that the rank of A, which is the dimension of the range of A, should be less than or equal to P, the dimension of the FP space. It is clear that the range of A equals to the whole FP space if and only if the rank of A equals to P, because if the rank of A is not equal to FP, then that means that there exists a vector U which is in FP but not in the range, and then adding U to the basis of R at the range of A, we could have a larger basis and hence larger dimension with still inside FP. So this kind of argument was used in a previous theorem on the dimension for matrices, and that was in part 2. The right invertibility part, suppose that the range of A equals to FP, then the equation axj equals bj, where j goes through 1 through p, these are solvable for every choice of the vectors bj, because that's what the range of A equals to fp means, that any fp vector can be written as some vector xj multiplied by A from the left. So then in particular, as a special case, we choose bj equals ej, the standard unit vectors, or we also call these the column vectors of the identity matrix, and in this case the identity matrix of size p by p that we are talking about. So if we put together as a matrix all these vectors, the ax vectors on the left, and on the right the b vectors b1 through bp, which are in this special case e1 ep, then what we get is the identity matrix. And that means that this matrix X that consists of the columns x1, xp is actually the right inverse of A. So this is one direction. When the range equals to fp implies that A is right invertible. And actually it's not just shows that A is right invertible, but it has a formula for the right inverse that we actually use in calculating the inverse matrix. Conversely, if A is right invertible, that means that AC equals IP for some matrix C, which should be of size, if A is P by Q, then C should be of size Q by P. Then that means that X equals to CB is actually a solution of the equation AX equals B for every choice of B. Because when you multiply with AX, you get ACB, which is just the identity times B, so that equals to B. So that means that this AX equals B is solvable for every choice of Bj, and that means that the range of A is the whole FP space. And this completes the proof of the first part. For the second part, about the nullity, or the null space. The null space of A equals to just the 0 vector if and only if the rank of A equals to Q according to the Rank-Nullity Theorem. And then according to the previous theorem on the Hermitian of a matrix A, we have that the rank of A equals to the rank of the Hermitian transpose of A. So that means that the rank of A equals to Q if and only if the rank of A H equals to Q. Then we have that this means that A H, the Hermitian transpose of A, is right invertible if and only if, based on part 1, on right invertibility. And then we have that the original matrix A is left invertible if and only if, using the transpose property. And again, we will use this later to calculate the left inverse using the right inverse of the transpose. So both of these parts actually contain some important techniques. One is that the inverse of the matrix A can be obtained by solving AX equals the identity equation, column by column, to get the columns of the inverse matrix. That's for the right inverse of A. And for the left inverse, we will use that the left inverse of A is the same as the right inverse of A transpose, or in this case, the A matrix is left invertible if and only if the AH Hermitian transpose is right invertible. So this actually proves the second part. To prove the third part, from parts 1 and 2, if A is both left and right invertible, then we have that the rank of A equals to P and that equals to Q. And we have showed this in the previous proposition about left and right invertibility, that the two one-sided inverses coincide in this case, and that they are unique. And with this we obtain all three parts of the theorem. So as an example, let's check the Rank-Nullity Theorem for the following matrix. And then we also find the range of A, or basis for the range of A and for the null space of A. So this is a 3 by 5 matrix. For the null space, we solve the equation AX equals to 0 using Gaussian elimination. And since the 0 right-hand side doesn't change, when we do row operations, it's enough to consider the augmented part only after we have the upper echelon form. So we don't start with the augmented part in this case, we only use the 0 augmentation at the very end. If it wasn't the 0 right-hand side, then we would have to use the augmentation from the beginning to solve the equation. So let's look at the matrix A. We want to have a pivot in a 1-1 entry, so for that we have to change a row at least. For example, let's change row 1, switch row 1 with row 3, that would be permutation. We wrote out before what this permutation matrix would look like, but let's not do this anymore, let's just do the elementary row operations. So switching row 1 with row 3, we get this new matrix. And then we want to eliminate the entry under this 1-1 entry. So for that, we subtract row 1 from row 2 to get +1, -1 cancel out. And we are subtracting -2, so we are adding 2 to -3, we get -1. Then subtracting 4 from 6, we get 2. Subtracting -1 from 1, I'm sorry, I skipped this one. Subtracting 2 from 7, we get 5. And subtracting -1 from 1, we get 2. And this matrix is already in upper echelon form, so we don't have to continue the Gaussian elimination. We can now augment it with the 0 right-hand side, and we can consider it as an equation and start solving it from the bottom to the top. This is the augmentation part, and let me remind you that the columns correspond to x1, x2, x3, x4, and x5. So starting with the last row, this means 1, 2, 3, x3 minus x3 plus 3x4 equals to 0. And from here we solve for x3 equal to 3x4. Then we go to the second row, the previous row. This means minus x2 plus 2x3 plus 5x4 plus 2x5 equals 0. Then we plug in x3 equals 3x4. The others are free variables. And what we get is that x2 equals 6x4 plus 5, 11x4, and 2x5. And the signs are correct. Make sure that you don't make sign mistakes. After this, after we have x3 and x2 in terms of x4 and x5 free variables, then we go to the first row, which says that minus x1 minus 2x2 plus 4x3 plus 2x4 minus x5 equals to 0. Then we plug in x2 and x3. And then from here we get x1 equals to let's see, I think I'm missing x5. I have 22x4 plus 12x4, that's minus 10 plus 2 minus 8 on the other side, minus 8x4. And then we have minus x5, and this would be minus 4x5. So this is minus 5x5. and switching sign twice, it stays minus 5x5. And note that this already shows two free variables, x4 and x5. And that means that we will have two basis elements for the null space. That means that the dimension of the null space is 2. Then the Rank-Nullity Theorem says that the dimension of the null space and the rank of A equals to 2 plus the rank of A equals to 5, the number of columns of A. And that means that the rank of A is 3. This can be also confirmed by seeing three pivots in the upper echelon form. So that means this is the same as the rank of the matrix. So finding a basis of the null space of A, let me correct the missing minus 5x5. We write this in a vector parameter form, and then we separate the x4 and x5 parts. There should be no constant part in this case, and we get two matrices, two vectors that form a basis for the null space of A. To find the basis of the range of A, this will be the first three pivot columns of A, because that's where the pivots are. And this is in the original matrix, so we use those columns: 0, minus 1, 1, 0, minus 3, minus 2, and minus 1, 6, 4. So the next section is about square matrices. These are just special cases of the general theorems. The main theorem is that if A is a P by P matrix, then the following statements are equivalent. A is left invertible, A is right invertible, the null space of A is just the 0 vector, and the range of A is the whole FP space. So everything implies everything here among these four statements. This is really just a corollary of the previous theorem for this special case. So what we have is A is left invertible if and only if the null space is just the 0 vector. But then we have that this is the case if and only if the rank of A equals Q, but Q equals to P, and rank of A equals to P if and only if A is right invertible, if and only if the range of A is the whole FP vector space. Note also that the part where we say that the null space equals to the 0 vector, that means that AX equals to B cannot have two solutions, because if we have like AX1 equals AX2 equals B, then if you subtract these from each other, we get AX1 minus X2, because the multiplication with A is a linear operation. We get that it's B minus B, which is 0. And that means that if the null space of A is only the 0 vector, that means X1 minus X2 should be 0, so X1 and X2 should be the same. That means there is a unique solution. The part that says that the range of A is the whole FP space means that there is a solution to AX equals to B for all B vector in the FP space. So what we have is that the range of A equals to FP if and only if the null space equals to 0. With other words, reformulating it using this uniqueness, so we cannot have uniqueness, we cannot have two solutions, that means the solution is unique. It's now equivalent to saying that there is a solution. Okay, so what we have is that for A P by P matrix, if the equation AX equals B has at most one solution, then it has exactly one. And that should be at least one. Has at least one solution, then it has exactly one. And by the way, this is also called a Fredholm alternative. One of the useful applications is that lemma that says that if A is a P by P matrix and B is a P by P matrix and AB is invertible, then both A and B are invertible. So note that these are all square matrices, and AB is also a square matrix, P by P. And we discussed these before, but it is always useful to repeat the arguments. The range of AB is a subset of the range of A, because if Y is in the range of AB, then that means that for some x, we have Y equals to ABX. And that means that we can remove the parenthesis from around AB and rewrite it as A times BX. And that's automatically in the range of A, since it says that A is applied to some vector. So what we have is that if Y is in the range of AB, then Y is also in range of A. We also have that the null space of AB contains the null space of B, because if X is in the null space of B, that means that BX is 0, and then ABX equals to ABX, which is A0, and we know that a matrix multiplied by the 0 vector is always 0, and that means that X is also in the null space of AB. So with this, what we have is that P, which is the rank of AB, is less than or equal to the rank of A, and that's less than or equal to P. And also we have that the 0, which equals to the dimension of the null space of AB, is greater than or equal to the dimension of the null space of B, and greater than or equal to 0 if we have invertibility. And then from these inequalities, what we obtain that rank of A equals to P, and the dimension of the null space of A is 0, and also similarly the dimension of the null space of B is 0, and the rank of B equals to P. And with this, the previous theorem applies, which means both A and B are invertible, both from the left and from the right. And we had the previous lemma saying that if this is the case, that both left and right inverse exist, then the regular inverse also exists, and it's unique. As an example, look at this problem where we have A P by Q matrix and B Q by R matrix, and we have U1 UK, a basis in RB. Then what we get is that AU1 AUK is a basis in the range of AB, if and only if the range of B intersection with the null space of A is the 0 vector. So for the solution of this problem, well, it's really kind of the proof. If Y is in the range of AB, then that means that Y equals to ABX for some X in, let's see, what should be X in. So A is PQ, B is QR. That means X should be in FR. It should be an R vector. And then since BX is in the range of B, and U1 UK is a basis of the range of B, then what we have is that BX equals to a scalar combination, a linear combination of the basis vectors U1 UK for some coefficients C1 CK. Then what we have is that Y, which was ABX, is really A times, and the BX can be rewritten as the sum as j goes from 1 to k of Cj Uj. Then because matrix multiplication is a linear operation, we can take it inside, and we get that this is the sum as j goes from 1 to k, Cja Uj. So what does it mean? This means that if we have something in the range of AB, like Y, then we get that Y is a linear combination of these AUG vectors. So that means the range of AB is in the span of these AU1, AUK vectors. Also, since u1, uk is in the range of B, it's a basis for it, we also have that the span of AU1, AUK is in the set AB, because U1 is in B, in the range of B, and UK is in the range of B. And then what we have is that the span of AU1, AUK equals to the range of AB, since we have the subset in both directions. So far this has nothing to do actually with the range of B intersecting with the null space of A. So what you see here is that this is true always, that the span of AU1, AUK, if U1, UK is a basis in the range of B, is actually equal to the whole range of AB. But now, for this AU1, AUK to be a basis, not just span it, a spanning set, to be a basis for the range of AB, we also need that AU1, AUK set is linearly independent. So we have that this is linearly independent if and only if the linear combination equals to 0, if and only if all the coefficients alpha 1, alpha k equals to 0. This can be also rewritten with A factored out. So this means that A times the sum as I goes from 1 to k, alpha I ui equals to the 0 vector, if and only if all the coefficients alpha 1, alpha k are 0. And that means that this vector, sum alpha I ui, is in the null space of A, and it's also in the range of B, if and only if all the coefficients are 0. That means that this is the case if and only if only the 0 vector is in the null space of A intersected with the range of B. All right, so with this we get this result. Another example, if you want to find a P by Q matrix A and a vector B, P vector B, such that the null space of A is 0, and let's just work with the real numbers right now, and yet the equation AX equals to B has no solution, so you should really look at this and see that how these previous lemmas and theorems applied. So we had, for square matrices, we had that the null space having only the 0 is equivalent that the range of A is the whole P space. That means that all right-hand side B's have a solution. The linear system AX equals to B. So now you can see that it's important to have square matrices, because if it's not square, we might have the case that the null space is 0, yet the AX equals B equation has no solution. So how can we figure this out, that AX equals to B has no solution? That means that the range of A is not the whole P space, and that also means that the rank of A, which is the dimension of the range, is supposed to be less than P. So based on the Rank-Nullity Theorem, the null space of A is 0 means that the rank of A equals to Q, because the null space has dimension 0, and that means that we can find we have to find P by Q matrix with rank of AQ less than P, and such that the null space of A is 0. So in general, you can consider then a matrix A where we have less columns than rows. And let's say that at the top we have the identity matrix, and then the bottom is just zeros. And we can have more 0 rows here because Q is less than P. So we have more rows than columns. Then AX equals 0 if and only if So if you substitute A with this matrix, this is kind of a block matrix, and we multiply this X vector, which is actually size Q, then what we get is that X1, XQ in the top because of the identity, and then at the bottom, when you multiply with the 0, you get the 0 part. And then we need that this is the 0 vector, and we have that this is the case only if the whole X vector is 0. So with this, what we obtained is that the only way that X is in the null space if X is the 0 vector. That means the null space equals to the 0 vector, set with the 0 vector only. Then, since the last PQ entries of AX is always 0, no matter what X is, in particular the very last entry is 0, that means that if we choose any vector B with the last entry not 0, for example all zeros but the last entry is 1, then this has no solution because AX will have always a 0 entry here where it's supposed to be 1. A more specific example, if you want to understand it, maybe through examples. If A is the 1, 0 matrix, it's a 2 by 1 matrix, and B is 0, 1, then AX equals to 1, 0, X, and X is actually now a scalar, a vector with one component, that equals to X0, and this equals to the 0, 0 vector if and only if X equals to 0, which means that the null space of A is 0. But then if you want to solve this special equation with this B01 right hand side, the AX equals to B equation, that means that you want to solve this 1, 0, X, which is X0 equal to 0, 1 equation, which is impossible, but no matter what X you choose, 0 is not equal to 1. So this has no solution. Some more specific examples to find the inverse of a matrix. So I mentioned this in the previous theorem already, that the way we can get the equation AX equals to I solved for the inverse matrix A inverse, which is in this case X, is that we augment the matrix A with the identity, and we use Gaussian elimination, elementary row operations, until we get on the left part the identity matrix, and then we have the inverse on the right hand side. So starting with the augmented matrix, where A is augmented with the identity matrix, then we start Gaussian elimination. You have to pay attention to use a modified version so that you don't have to use fractions. So for example, instead of adding 1/3 of the first row to -1 times 1/3 of the first row to the second row to cancel 1, instead of that, what you can do is subtracting the first row from 3 times the second row, because then you get 3 minus 3. 0, then we get 3 times 4, 12, minus 9, 3, and 3 times minus 10, minus 30, minus 22, that's minus 30 plus 22, minus 8. Then on the left hand side, this is 0 times 3 minus 1, so it's minus 1, then 3 and 0. We can also do the same thing with the third row, 3 times the third row minus row 1, so that this entry gets zeroed out. Then we get 0, 0, 1, minus 1, 0, 3. Then from here, this is actually called the Gauss-Jordan elimination, when you don't stop here and start solving it, but instead of that, we start going upward and we cancel out the terms above this pivot. So for this, what we need is we have to cancel out minus 8. So what we do is we add to row 2 8 times row 3. Because then we have minus 8 plus 8, and that becomes 0. Note that because of these zeros, this part doesn't change anymore. So we only have to do to the right. Then we have this in row 2 plus 8 times row 3. So minus 1 minus 8 minus 9. Then 3 plus 8 times 0 is 3. And 0 plus 8 times 3, 24. We also zero out the minus 22. So this becomes 0 if we add 22 times row 3 to row 1. Again, these parts do not change because we have zeros here already. So 22 times 0 in the row 3 doesn't affect these entries. But then we have to go and also modify these entries. So we have row 1 plus 22 times this. That means minus 22. So it's minus 21. Then 0 doesn't change anything, 0. And 0 plus 22 times 3 in row 3, that's 66. So then we have this matrix, and now we continue to the next pivot up from this pivot, and we zero out the entry above it. Under it we already have 0, but now we make it 0 above it. For this we need 3 times this row subtracted from this row. Row 1 minus 3 row 2. So that becomes 9 minus 3 times 3, that's minus 9, 0. The 0 part and the 3 part doesn't change because you are multiplying 0 with minus 3. But then this minus 21, 0, and 66 changes. So we have that for minus 21, you add minus 3 times minus 9, that's 27. Minus 21 plus 27, it's 6. Then 0 minus 3 times 3, that's minus 9. And 66 minus 3 times 24, that's minus 72, that's minus 6. So now we have a diagonal matrix here. And in order to get the identity matrix, all we have to do is divide the first row with 3 and the second row with 3. So this should be also 1. And with this we get here the identity matrix. And that means that whatever it's here is the inverse of matrix A. Again, this was obtained by augmenting the matrix A with the identity matrix of the same size and then doing Gaussian elimination, but actually going also backward to make the whole left-hand side equal to the identity matrix. And then on the right-hand side, we get the inverse of the matrix A. By the way, it's also useful to check that there is no mistake and you really get A times A inverse equals to the identity matrix. Next example, we talked about left and right inverses, so let's find the right inverse of this 2 by 3 matrix. So the right inverse is supposed to be a 3 by 2 matrix X, such that when you multiply them together, you get a 2 by 2 matrix, which is supposed to be the identity if X is the right inverse of A. And the way we get X, for example, is if you use the augmented matrix A and I, where the identity matrix is the 2 by 2 identity matrix. And we use Gaussian elimination. Again, we can avoid fractions by using least common multiple. So in order to zero out 7 using the first row, what we do is the least common multiple of 2 and 7 is 2 times 7. So to get 14, we multiply the second row with 2, and the first row with 7. And then in this case we get 14 minus 14, 0. We do the same thing with the other entries. So 2 times minus 3 minus 6 plus 7 is 1. Then 2 plus 7, 9. And 2 plus 7 is 7. And then 2 plus 0 is 2. And this is already in echelon form, upper echelon form, so we cannot just continue the previous way. We're never going to get the identity matrix, although we could get similar thing. But instead of that, in this case, let's just start solving it from the bottom to the top, like we always do with Gaussian elimination. So because we are looking for a matrix X, 3 by 2 matrix, we actually, and also we have 2 columns on the right hand side from the identity matrix, we actually have 2 sets of equations. The first column of the right hand side corresponds to the first column of the right inverse. So that means this is the equation that whatever we have here multiplies x11, x21, x31, and that's supposed to be equal to 1, 7, the first column. And then the second column on the right hand side corresponds to the second column of the unknown inverse, right inverse. So that means if you multiply the original, not the original matrix, but this modified matrix with x12, x22, x32, the second column of the inverse, then it's supposed to result in 0, 2. So we write this in an equation form. For example, from this first one, the second equation is x21 plus 9x31 equals to 7, and from here x21 is 7 minus 9x31. We get a free variable. Then the first equation, minus 2x11 plus x21 plus x31 equals to 1. From here x11 is 1 minus 21 is 7 plus 9 x31 minus x31. Actually this is supposed to be plus x31, I believe. Oh no, so instead of changing the sign first, I just take it to the other side. So this is then minus x31, and then I divide the whole thing with minus 2. But then this becomes minus 6 over minus 2, which is 3, and 8 divided by minus 2, which is minus 4. From the second column, we have that the original matrix times the second column of the inverse, that means x12, x22, x32, should be equal to the second column of the right hand side, 0, 2. We rewrite this and we get that x22 plus 9 x32 equals to 2. From here x22 is 2 minus 9 x32. Then we get the first equation from the first row, minus 2 x12 plus x22 plus x32 equals to 0. And from here x12 equals to minus x22, so minus 2 plus 9 x32 minus x32 divided by minus 2, which means it's 1, and minus 4x32. So that means that we have infinitely many right inverses because we have free variables x31 and x32. And right inverses actually have the form 3 minus 4x31, 1 minus 4x32, 7 minus 9x31, 2 minus 9x32, x31, x32, with x31, x32 arbitrary. For example, for some specific case, if you want x31 equals -2 and x32 equals 3, then plugging in these values, we get the specific value for the right inverse in this form. And of course, you should always check that really A times A inverse is the identity matrix. In the next example, if you want to find the left inverse instead of the right inverse, then, for example, this is a 3×2 matrix, then note that the left inverse of A is the same as the right inverse of A transpose, and that's because of the property of the transpose that switches around the product. Maybe let me remind everybody to this property that A times A inverse. If you transpose this, you get A inverse transpose times A transpose. So that means the left inverse of a matrix is the same as the right inverse of the transpose, and vice versa. And that means that we can use the same procedure as before in the previous example. For the transpose, then we get the right inverse of the transpose, but if we transpose that, we get the left inverse of the original matrix.